Welcome to The Orbital Flywheel, where we explore the fascinating convergence of space, silicon, and intelligence. This presentation delves into a strategic analysis of the SpaceX, XAI, and Tesla integration, the implications of the 1 million satellite filing, and the ambitious path toward universal high income. We'll examine how these seemingly disparate entities are aligning to create a powerful, self-reinforcing system, fundamentally changing our technological landscape. Our core thesis revolves around building what we call the trillion-dollar industrial machine. This machine aims to consolidate energy, logistics, and intelligence to bypass traditional terrestrial constraints. The ultimate goal is to create a self-reinforcing AI feedback loop, targeting a combined valuation exceeding $2 trillion. SpaceX drives the logistics with its formidable lift capacity and optical mesh connectivity. XAI provides the intelligence through its advanced grok models and recursive training. And Tesla supplies the critical hardware, from AI chips and energy solutions like Megapack to the robotic labor provided by Optimus, forming a truly synergistic flywheel. The strategic rationale behind consolidating this empire is clear, particularly with the SpaceX-XAI merger. This move offers immense capital efficiency, leveraging SpaceX's substantial valuation to fund XAI's massive compute needs without external dilution. Furthermore, it creates a powerful vertical lock in XAI gains exclusive orbital infrastructure, while SpaceX secures an anchor tenant for its Starship launches. The transaction velocity has been swift, with merger sub-entities registered in January 2026, and a Dyson swarm concept confirmed soon after. This combined entity, already valued at over $1 trillion, is targeting an IPO valuation of more than $1.5 trillion by late 2026. However, terrestrial compute is rapidly hitting its limits. We face a looming supply gap as AI's power demand, projected to exceed available terrestrial power by 2035, continues to grow exponentially. This isn't just about energy, it's also a water crisis, with large data centers requiring tens of millions of gallons per year for cooling. Local governments are increasingly blocking new data centers due to grid constraints. Clearly, a new paradigm is needed to overcome these fundamental terrestrial barriers. This brings us to Project Orbital Compute, and the groundbreaking 1 million satellite filing submitted to the FCC on January 30, 2026. This isn't just an expansion of legacy Starlink, which has around 9,000 satellites. This new system proposes 1 million satellites within narrow orbital shells, connected by a petabit-scale optical laser mesh. Its function? To act as a floating cloud supercomputer, primarily for AI inference. As the SpaceX filing narrative suggests, this is envisioned as a crucial first step towards becoming a Kardashev 2-level civilization, capable of harnessing the sun's full power. The fundamental advantage of orbital compute lies in the thermodynamics of the vacuum. On Earth, we grapple with intermittent solar power, atmospheric losses, and the need for active cooling, consuming vast amounts of water and energy, with up to 40% of power going to cooling. In orbit, we have constant solar exposure, vastly improved capture efficiency, and the ultimate heat sink, the -270°C vacuum of space. This allows for passive radiative cooling, eliminating the need for water and fans. This physics advantage enables high-density compute without the terrestrial cooling penalty, a game-changer for AI infrastructure. Achieving silicon sovereignty is paramount, and Tesla's hardware roadmap is pushing the boundaries. AI5 focused on full self-driving and Optimus, with manufacturing handled by TSMC and Samsung. AI6, now 50% complete, shifts focus to Optimus and data centers, with Samsung's Taylor, Texas fab playing a crucial role. The ambitious AI7, or Dojo 3, is currently in its concept phase, specifically designed for space-based compute. This proprietary architecture is optimized for high radiation environments and solar efficiency, marking a significant decoupling from external GPU providers like NVIDIA, as Tesla moves from car chips to infrastructure chips. Speed itself is becoming a moat. While the legacy industry, like NVIDIA and Intel, operates on an 18 to 24-month chip generation cycle, Tesla Silicon has achieved an astounding 9-month cycle. This rapid iteration has profound strategic implications. It enables targeting the highest volume AI chips globally, spanning cars, robots, and satellites. It allows for co-design, meaning hardware is custom-built for Zeiss Grok models. And crucially, it facilitates distributed inference across millions of nodes, moving away from centralized racks to a truly distributed computing network. The logistics of deploying these megastructures in space rely entirely on Starship's capability to move mass to orbit. Starship can lift over 100 tons to low Earth orbit per launch, with a cadence of rapid reuse that enables. At the heart of this system is the intelligence layer, powered by XAI and Grok. This comprises a sophisticated compute loop. Training of the advanced Grok models occurs terrestrially on massive high-power compute clusters like Colossus II. Once trained, the models are deployed for inference across the 1 million orbital satellites, forming a distributed network for real-time, low-latency global AI processing. This intelligence is then beamed via optical links directly to edge applications, such as Optimus robots and end users, essentially making XAI, the ghost in the machine, for a truly global, real-time AI. The physical AI, represented by Optimus, heralds a profound labor shift. Tesla is targeting a production of 1 million Optimus units per year by 2027, with a scale goal of billions of units by 2040. The economic function of this automated workforce is transformative. It decouples GDP from population growth. As Elon Musk stated in a Q4 2025 earnings call, it will actually move the needle on US GDP significantly. This productivity multiplication leads to a near-zero marginal cost of labor, fundamentally altering global economic structures. This brings us to the endgame universal high income, or UHI. Unlike universal basic income, which operates within a scarcity economy, aiming for a poverty floor, and funded by taxes on human labor, UHI is predicated on an abundance economy. Its goal is prosperity and thriving, funded by a productivity dividend from the automated workforce. As you can see in the graph, human labor income, capped by time, is eventually surpassed by the automated output dividend, which is capped only by compute. This marks a critical inflection point, fundamentally redefining the relationship between work, income, and human prosperity. However, this ambitious undertaking comes with critical risks. Orbital congestion is a major concern. 1 million satellites significantly increase the risk of Kessler syndrome, and over-reliance on automated collision avoidance creates a single point of failure. Spectrum wars are also on the horizon, with potential interference with radio astronomy and rival constellations, leading to regulatory battles over thousands of pending satellite expansions. Finally, geopolitics poses a significant threat. Countries like China are already responding with gigawatt-class space infrastructure, viewing low Earth orbit as strategic territory, sparking a new space race with initiatives like Guowang and Qinfan. We must also consider the environmental paradox. While orbital compute offers a solution to Earth's looming water crisis by saving billions of gallons, it introduces new atmospheric challenges. Re-entry pollution, estimated at 3 million kilograms of aluminum oxide per year, could lead to ozone layer depletion and alter atmospheric chemistry. There's also the issue of visual pollution, impacting ground-based astronomy and the pristine night sky. This presents a complex trade-off, moving pollution from Earth's terrestrial environment to its upper atmosphere, demanding careful consideration. In conclusion, we are charting the path to Kardashev 2 and a new infrastructure paradigm. Our first key takeaway is that vertical integration is paramount. From chips to launch to robots, only a unified ecosystem can achieve this unprecedented scale. Second, space is undeniably the future of compute. Thermodynamics dictates that high-density AI infrastructure must leave Earth to overcome cooling penalties. Finally, the challenge shifts from production to distribution. With an abundance economy, the focus moves to distributing access, leading to the universal high-income model. The flywheel is spinning, and this profound transition has already begun.